Welcome to our discussion about data communication, sometimes called networking or telecommunication. I really love this topic. I've taught for many years the advanced course in data communication. It's a really fun one. We're going to dive into it, not at a super great depth, but we're going to have some fun talking about it. From an administrative perspective, let me remind you that the programming project is due, so make sure to check the deadlines and make sure you get it in. And then also we're going to be working quite a bit on the database project next. In fact, in the next couple of classes, we're going to be meeting in the computer lab to work on the database project. So make sure to check the syllabus. For those who are in sections 1 and 2, we'll be meeting in the basement of the ARC building, which is the building between Tahoe Hall and the Union. We're meeting down in 1016 for both the next couple of classes. For section 3, we've talked about this. We'll be meeting in Mendocino Hall, 2007, and then we'll be meeting in Folsom Hall, 1029, which is right kind of straight out past the front door on the 6th. And we'll talk in class about the shuttle and all the things with that. But make sure that that you know where to go for the next couple of classes. Now, after that, we're going to be having our net neutrality debate. So net neutrality is a controversial topic that we will be discussing as part of this this discussion of networking and telecommunication, because it's an important one that affects a number of different businesses and you. And then after that, we will talk about enterprise systems. So make sure that you do the readings for enterprise systems. So this is kind of a sketch of what's going on. Make sure to check the syllabus for the exact dates, but this is what's going to go on in the next little bit. Again, I'm not able to embed this copyrighted video in our class videos, but if you just search on YouTube for Moss introduces Jen to the internet, or go to the link here, and I'll try to put a link also next to this video, you'll be able to watch this 3-minute video and try to figure out what is the internet. So I want you to pause the video for a second, think to yourself, without looking on Wikipedia or Google or something like that, what is the internet? How would you define it? What does it mean when we're talking about the internet? Think if you can figure out what that is, because it's important, figuring out what exactly is the internet. So let's talk about that. We're going to get to the definition of the internet a little bit later. First of all, why do I care about networks in general? Why do we need them? Why are they important? Well, as we've already discussed, one of the really important reasons is data or information. MIS, Management Information Systems, are all about information, and today we just need to transfer data or information all over the place, and we do use networks to do that. Recently, for example, I've had internet connectivity problems due to a storm at my home, and it's frustrating. We don't have access to the information that's available on the internet because our networks aren't working. So let's talk about some of the basic things. So we have, in networks, we have clients, servers, and circuits. Those are all very basic components. A client is a device that that connects to the network and accesses the data, requests the data, downloads the data. These things can be desktop, laptops, tablets, netbooks, cell phones, whatever it happens to be. These are devices that ask for and get information from the next one, which is a server. So a server is a device that serves up information or provides data to clients over the network. And the circuit is the connection between those clients and the servers. Now we can go in a little more depth on this. Here's some example of clients. We've got tablets and little old beige boxes and phones and a nice little Skyrim battle station with lots of monitors. But all of these are devices, clients, that can request information from servers. We also have servers, okay? Here's some example of servers. Now, as it turns out, these are all hardware that we're looking at in the last couple of slides. And so all of these could have software that acts as a client or acts as a server or both, but typically our clients tend to look a little more like this, and our servers tend to look a little bit more like this. Just because servers, it's easier, the picture on the left shows a server rack in a data center, and it's just easier to power and to cool and to manage servers when they're in particular configurations. The image in the center is a blade server, and the image on the right is a server that looks a little bit more like a desktop. We also, as part of our circuits, or in between our circuits and our clients and servers, we have something called a network interface card. These are the cards that go into our laptops, desktops, tablets, phones, etc., that connect to the network. And so we'll talk more about layers in a little bit. Nowadays, these are mostly built into our motherboards on our devices, or on chips that are similar to that. But you can still buy separate cards, like the image on the right, to connect a network interface card, your device, to the network. Circuits also come in all shapes and sizes, and I'll bring some show and tell next time. But here's some example of circuits, either well managed and groomed or complete haywire. Another device that is related to our circuits, sometimes part of our circuits, are these devices called hubs and switches. Now, hubs are becoming a little less common because switches are superior in almost every way, but these help us to connect different cables from different devices together. Okay, and when signals are sent through one circuit that connect at these hubs and switches, they kind of act a little bit like a repeater or a switchboard, sending the signals out the other circuits as needed. So here's a little example of components of the network. On the left-hand side, we have some servers. Now, these are represented just by computers' images. On the right, we have some clients. In the middle, we have a switch. And then the blue lines represent connection circuits in between those devices. And then we also have a router. We'll talk more about routers in a little bit. So when we define networks, one way that we can define them is in terms of their geographic scope, in terms of how large or small a network covers in terms of space. One of the most common types of networks is a local area network, sometimes abbreviated or talked about as LANs. A LAN covers a fairly small amount of space, usually a house or a building, or sometimes a section of a building, a fairly small space. Sometimes we have networks that are a little bit bigger than that sometimes we call campus area networks. Now, our college campus, you could define it as a campus area network, but also other big organizations like the Microsoft or the Google campus with multiple buildings that are connected together, multiple local area networks in a limited geographical space, all on one piece of property. That would be called a campus area network. And then we also have wide area networks. Now, wide area networks have they've merged and changed quite a bit over the last 20 years, but the general idea is that these are networks with a large geographical scope. They connect LANs together across a long distance, maybe dozens, hundreds, or even thousands of miles, and kind of the defining feature is that we're crossing property or space that isn't necessarily owned or managed by our organization. So maybe it's in the next town over, or the next state over, or the next country over, and that's connecting using wide area network technologies. So here's a little example here. I'm going to kind of focus most on the top image and the one on the right and the one on the bottom right. Here's an example of a local area network in the top left, where we have a switch surrounded by some servers and some clients. This is just a simple local area network. And this happens to be inside of one of the buildings at an Air Force base. Okay, and at an Air Force base, this one happens to be McClellan Air Force Base in the Sacramento area. And each building might have its own network, okay, part of a backbone or a campus area network. And that network might connect to other networks across the country using wide area network technology. So the bottom right shows a picture of connecting cross country with wide area network technologies. And here's another image of a different network that might connect using wide area network, okay, across a couple different countries. One of the really important principles or concepts or frameworks that we talk about in terms of networks is this idea of layers. Kind of like layers on an onion kind of layers, actually. And the layers help us to define the functionality of what the network hardware and software is doing. I'm going to go into a little more detail on that. But there were two proposed models. One that was kind of the official academic proposed model, the OSI model, or Open Systems Interconnection Reference model, which is quite the mouthful. That model is still in use today in some places, but realistically, it isn't exactly how real world worked. And so the real world kind of, networks evolved and became the internet, and the model that showed up and kind of became the industry model, the one that worked and the one that won, is the internet model. So we'll see that in the next slide. All right, so here's the two models. The OSI model's on the left, the internet model's on the right, and there are some differences here that are a little bit more than, I'm simplifying away a few differences, but the main difference is that in the OSI model, the top three layers are separated by some functionality, whereas in the internet model, that's all kind of smashed together. The idea was that, network people are going to deal with these bottom four layers, and software developers, the application people, are going to deal with the top layer, the application layer. And yes, the application layer does include the application software, the presentation, the session, but realistically, we're just going to call that the application layer in our discussions going forward. So we're going to use the internet model in our rest of our discussion and on the exam. All right, so let's talk about the different layers and what they do. We'll start at the top. The application layer, again, this is where the programmers build software. It's where people access the network to do stuff. Okay, so in some types of software, we have the application layer, in your web browser. It goes out to the internet and it gets web pages and video files and songs and pictures, and it displays web pages. All right, so it uses the network to do that, and it uses some software like HTTP. We'll talk about that. There's other software, maybe your Spotify application. It uses the network to get music and to stream music for you and to get images and things like that. And so the application layer is everything involved with a network that the application is using to perform work. Now, the other four layers, like I said, have to do with the software and hardware that your computer is doing just to make networking work on your computer. We separate it by functionality so that we can fix things and replace things, and we'll see that. So layer 4, the transport layer, it's all about getting a message all the way to its destination, making sure that it is reliable all the way to the end. Okay, as it goes through different routers and other people's networks and across the internet, we wanted to make sure that we get it all the way to the other end. Now the transport layer also does a couple of other things. It makes sure that we connect all of the network layers, the bottom four layers, to the fifth layer, the application layer, so that we're, keep making the network work for the software that we're using. It also takes care of what happens if we need to send a message that's really big, too big to send in one message. Well, it chops up big messages into smaller pieces and then puts them back together again. And it also is in charge of what happens if our network connection is really slow or really fast. How do we manage the flow of the different pieces of information that we're sending? So the transport layer also deals with that. Layer 3 deals with routing, and in particular something called addressing, which we'll talk about an IP address in a minute, but routing, the path that a message takes throughout the network. Layer 2 is all about getting a message just to the next device. So between your device, tablet, phone, laptop, and the wireless access point that it's connected to, or to your router. So it just is involved in making sure that it gets to the next place. Now, it also controls the hardware and formats the message a little bit and does some minimal error checking, but its main job is just to get the message to the next device. And then the physical layer is just the one that makes things into ones and zeros, or waves, as we'll see in just a minute. So let's take a very simple example in terms of how this works in the layers. We have, let's pretend your web browser. We're going to go to a website. All right, maybe we're going to the university's website. So your web browser creates this message, and it gets formatted in a very particular way, in an HTTP format, Hypertext Transfer Protocol. You don't need to know that. But it gets formatted in a very particular way that web browsers and web servers understand. Kind of like their own language, okay? We call them protocols, but it's like speaking a different language. So your web browser and your web server understand the HTTP language, all right? And so they make a special message that says, hey, give me the web page that's at the university's main website. And that message gets handed by your browser to some software on your computer that does the transport layer. Now, most people use TCP on your computer. It's by far the most widely used language or protocol at the transport layer. And so our message goes from the application layer and it gets encapsulated or put in a TCP segment. And then that TCP segment gets handed off to another piece of software on your computer called the Internet Protocol, or IP, and it gets encapsulated and adds some information there. Some of the information that gets added, for example, is the IP address that's used for routing. And then it gets handed off to another piece of software on your computer called Ethernet, and gets encapsulated and adds things like, if you've ever dealt with something called a MAC address, MAC addresses get added to our message here. And then finally, we send it over to our hardware, and the hardware is responsible at the physical layer for turning that into ones and zeros. Oftentimes, if we're on a wired connection, we're talking about voltage levels, okay? Ones and zeros represented by volts of electricity. Or maybe we're talking about waves, if we're talking about wireless, or talking about cable modems, for example. We're talking about waves, electrical waves. Either way, the physical layer is all about sending that to the next device. Whoops. And so we send that to the receiver. The receiver's physical layer then knows how to translate that back up so that the data link layer can understand it. Data link layer looks at the MAC address and all the other Ethernet stuff on it, takes it out of its message, sends it on up, and continues to send it up and to send it up. And so at the recipient side, it passes through a number of different layers of software and the hardware layer at the physical layer until the server gets that and says, oh yeah, I understand HTTP. I know what to do. Let's send the web page back and all of the images back to the recipient. And so that happens. The process goes in reverse, and it happens multiple times for every single file that needs to be sent, all millions of times per second. All right, here's what happens. All right, so let's talk a little bit more detail about some of these ideas. So TCP and IP were originally developed as kind of one big protocol. They've since been kind of sort of separated, but they still work very closely together. Developed as part of the DARPA project, which is the predecessor to the internet, by these gentlemen, Bob Kahn and Vint Cerf. And this protocol dominates. It's pretty much a requirement to participate in the internet to use TCP and IP and the related technologies. The next one is the layer 2, the data link layer. It was built by, or invented by Bob Metcalf at Xerox PARC, the Palo Alto Research Center, and is the most common protocol for local area networks, and has become so good that it's actually starting to creep into wide area network technologies. And so I wouldn't be surprised in the next few years if most wide area networks started moving towards Ethernet as well. Now, as we move across the network, and this is maybe a little more complex, this is maybe probably not on the exam, but something to be aware of is, let's say we have our device over here on one side that has all 5 layers here, and we've got our recipient over here that we're sending our message to. As our message moves across the internet, it's going to go through a bunch of different devices, maybe switches, maybe routers, and each of those operates at different levels, and the message gets processed quickly, very quickly, by each of those devices, all the way to the destination. All right, so let's talk about the physical layer for a minute. The physical layer involves sending messages, ones and zeros, using waves and using, digital streams of information, sometimes light pulses, most of the times electrical pulses. And we can have a bunch of different physical layer cables. And I'll bring some show and tell on this. This is twisted pair cabling. So twisted pair cables are the most common. They are literally twisted pairs of wires that are then bundled together and put in an outside sheathing. The twists help to reduce problems with electromagnetic interference. These are widely used in local area networks. In fact, they're kind of almost the only thing used in most local area networks. They're widely used for telephone wires, and they can also come in a couple of varieties. They can come in shielded, or unshielded. The shielded means they put a foil shield around the bundle of wires before they put the outer plastic shielding on it, or sheathing on it, and that helps to reduce electromagnetic interference also. The next cable you might have seen before is sometimes just called a cable, but realistically it's coaxial cable, or coax, and this is widely used in cable television and cable internet. It's an okay cable. We've kind of dealt with it, even though it's much more expensive than twisted pair cabling. You'll notice that it has a single kind of larger core of copper surrounded by some plastic, and then a foil shield, and then this kind of lattice of shielding here, and then an outer plastic as well. And it's an okay one. Because of all of this extra shielding in here, it actually gets some decent range, but it's kind of expensive. And so realistically, the only major reason why we keep using it is because it's already in most houses and apartments in this country and in many other countries as well. And so that's kind of one of the main reasons we keep using it. New installations tend to have a lot more twisted pair cables. Now the next one is fiber optic cables. Fiber optic cables are usually glass cables that are very, very thin, and light is transmitted down the cables, and they're really, really good for a few reasons. They travel for a long distance without signal degradation. They are exceptionally fast because we're talking about close to the speed of light. And they also don't deal with or don't have the problems of electromagnetic interference like twisted pair and like coaxial cable. And so they can be used in some places where there's heavy machinery, for example. The problem is they're just more expensive. So all of the pieces involved are more expensive, and they're a little bit more difficult to install because cutting and terminating, putting the ends on fiber optic cable is just a little bit more involved than doing it with copper. Now that brings us next to our wireless, our radio communication. So Wi-Fi has become very common. Wi-Fi is for wireless local area networks, and each device on the network has to have a radio transceiver to send and receive messages. Here's a very simplistic wireless router, which realistically is a router plus a switch plus a wireless access point all in one device. Why do we like Wi-Fi? Well, it's just really convenient, and we don't have to worry about putting in new cabling if our building doesn't have it, or upgrading it. We can just upgrade the wireless access point in the device. We also have microwave communication. So microwave communication is kind of akin to the cable example a little bit ago. It's decent for medium range wireless. It requires line of sight. Okay, so it has a maximum range because of the curvature of the Earth. You know, it's somewhere 25 to 30, 40 miles is the maximum before the curvature of the Earth makes line of sight not feasible unless you have another antenna in between. But it's decent speeds and decent range. Google's actually experimenting. They bought a company to start moving towards kind of line of sight, high-speed internet, even to consumers and to apartment complexes and things like that. So we'll see probably microwave and related technologies take off a little bit more in the next few years. And then, of course, we have satellite. Satellite's a special form of microwave communication that we're obviously pointing towards outside of our atmosphere and in the upper atmosphere with satellites and with, you know, our Mars rovers and Voyager space probes and things like that. But the challenge here is something called propagation delay. So for those of you who are gamers out there, you'll recognize that, hey, pings are pretty painful. Ping is the delay between the time that you send a message and get a response. And that can cause problems in some types of communication. And when we're sending things to another planet, or in the case of something like the Voyager space probes, receiving information from possibly outside of our solar system, it just takes a long time, minutes or even longer, to get the message back, and that causes some challenges. So when we transmit, here's the electromagnetic spectrum. You can see kind of the, here's where X-rays come in, here's where the UV rays that we have to worry about skin cancer on, here's our visible light spectrum, infrared if we've got a television remote, for example, our radio waves, FM and AM. And then we've got this huge section called microwaves. And yes, you're also talking about your microwave oven, but we're mostly not talking about the microwave oven. We're mostly talking about waves that just happen to be shorter wavelength than FM and AM, but longer than infrared and these others. And these waves, there's some certain ranges that tend to be really important. So the 2.4 and 5 gigahertz ranges tend to be really important because those are used in most countries for unlicensed use for devices. So that's why we can have wireless routers and baby monitors and wireless phones and things like that, because they all use this particular range because it's legally allowed to do so. But we also use certain ranges. Here's, for example, some of the most common cell phone frequency ranges that are really important, but those ones require licensed use. And then there's other ranges for emergency responders and other sorts of licensed frequency ranges. And most of those are also in the microwave range because these are really useful ranges. All right, so what I want you to do is take a minute, answer some questions about cabling, and then we'll come and talk about this a little bit more after we talk more about cables in our next class. Now, we've already started to get into digital versus analog. I talked about how digital transmits discrete binary values, ones and zeros. We've talked about binary. Whereas analog communication is waves. And so if you remember from kind of your high school physics classes, we've got waves have different characteristics. They've got the amplitude of the wave with the height of the wave. They've got the length of the wave, or the wavelength, the frequency of the wave, which is the inverse of the wavelength. And those are all really important. And then we have on the left-hand side, we've got our ones and zeros that we can send using discrete values, and in this case, voltages. Now the trick is how do we then switch back and forth between those? We'll see that in a minute. Another concept, though, is how do we transmit our information? In this case, do we transmit our bits at the same time? What if we had multiple wires, like in the case of twisted pair cables? What if we have multiple wires? Can we transmit these ones and zeros all simultaneously? Sure we can, right? So those get transmitted in parallel, okay, simultaneously, down one wire at a time. Or we can transmit the same bits sequentially, all one after the other after the other. So if you were to think for a second, think which of those is faster, all things being equal? Is it parallel or is it serial? Well, the answer is complicated. So all things being equal, parallel is much faster because you're transmitting more bits of information per time period. But here's the rub. We used to use, when we're hooking up printers to a computer, we used to use a really wide ribbon cable that was sometimes called a parallel cable, or a parallel printer port that we would plug it into, a big chunky cable. But now if you hook up a printer that's not wireless to a computer, it's usually using a USB cable, or a universal serial bus cable. So the old cable was parallel, but the newer cables are serial. Well, that seems odd to me, right? And then for those of you who are computer builders, you might realize, okay, well, what kind of cables did you used to connect hard drives with? Well, they were parallel ATA cables. Whereas now, if you're connecting a hard drive up, you usually are using a SATA cable, or a serial ATA cable. And so in both of those cases, we've gone from parallel in the past to serial cables now. Why might that be? Well, as it turns out, when we're transmitting in parallel, it's actually when we start ramping up this to having each of these time periods be in the millionths or billionths of a second, it's really hard to keep these in sync. Because what happens if one of those wires gets out of sync with each other? Then all of the data we're transmitting gets out of sync because each of those means different things. And so as it turns out, as we move up in speed, serial is actually easier to keep synchronized, and so a lot of our newer cables tend to use serial transmission, even though, all things being equal, parallel tends to be faster. All right, so we've talked about characteristics of waves a little bit. We've talked about amplitude and wavelength. There's also something called phase, and that's a little beyond the scope of this class, but we can also change that when we're transmitting data. So if we need to take ones and zeros and communicate them in an analog format, we do that by taking a basic wave, okay, that's just transmitted. Sometimes we call that a carrier wave. It has certain characteristics, and then we modify those. We can modify the amplitude or the height of the wave. We call that amplitude modulation. We can modulate the frequency of the wave. It's called frequency modulation. Or we can modulate or change the phase of a wave, phase modulation, or sometimes phase shift keying. In sound waves, if we're to modulate the amplitude, that means that the sound gets louder, okay, because amplitude is associated with volume. Frequency is associated with pitch. So if we're speaking in a higher voice versus a lower voice, that's we're modulating the frequency. And phase is doesn't have really a vocal analog with that. All right, so that's analog versus digital. We'll get more into that in my more advanced class. Let's talk wireless for a little bit. Here are the various Wi-Fi standards. And most of them are old at this point. Okay, the A, the B, the G, and even the N standard, which is still the most commonly used in practice, is actually technically obsolete. The standard is. So the current ratified standard is the 802.11 AC standard, and you can see, if you go to the store, the AC routers and access points are becoming more and more common. They're also becoming more common in our devices, our phones, our tablets that we're buying that become equipped. Technically, there's also a standard that's the AD standard, which is also current. That one is kind of a weird standard. It's only for certain purposes. Technically, it can be a little bit faster, but it's not really a widely used standard. And as we move over time, we're starting to look towards 2019-ish for the AX standard is expected to kind of succeed the AC standard as the next main standard. We'll see as that develops on whether it actually works and is faster and how fast they ended up making it. Over time, though, the transaction speed, which is the middle column here, tends to go up over time, and the frequency ranges that are used have kind of changed a little bit over time. We've used the 2.4 and the 5 gigahertz frequency ranges for a while. Some of the upcoming standards have also started using the 60 gigahertz frequency, which is useful unless you need to go through a wall or anything, and then that doesn't work because 60 gigahertz doesn't go through walls. The 5 gigahertz standard actually doesn't go through, or frequency range doesn't go through walls and buildings and things, as well as 2.4, which is why you tend to have a little longer range for 2.4 gigahertz and a little shorter range for 5 gigahertz. All right. Moving on to the network and transport layers, let's talk about this concept of routing and switching. This is about packet switching. So let's say we've got a message on the right-hand side that is from New York. So this message right here needs to get chopped up into 6 different pieces because it's so large, and it needs to be sent over to LA. This message could go through many different routes. Each of these red dots represents a router, and each router makes its own decision as to which path a message takes. So when the message gets sent to this router in New York, for whatever reason, this isn't very common, but for whatever reason, it has decided to send message or part 1 and part 4 down this route to Chicago. Parts 2 and 5 got sent down this route, which goes through Dallas, and then etc., okay? And then at each of these locations, these messages get sent a different direction, okay? For whatever reason, at Chicago, part 1 got sent directly to LA, whereas part 4 ended up getting sent to Dallas and then on to Los Angeles. And that's how the internet works today. It was designed well, strangely or not, for what happens if the President of the United States needs to send a nuclear launch code, and what happens if one of the transmission circuits goes down, is damaged, or doesn't function. Or what happens if they cancel the nuclear launch signal needs to be sent? How do we route around problems? And so IP and TCP were designed as part of the DARPA project to figure out how do we deal with that? What happens if a particular node or a particular circuit or router goes down? How do we route around problems? And so each router is constantly updating its information and sharing information with its neighbors so that it knows how to route messages properly and then reassemble them at the destination. Now, addresses. We've talked about addresses. The most important address on networks happens at the network layer with our IP addresses. These are really important. We're actually moving towards a different format for some IP addresses. These ones used to take 4 bytes. They're going to take more in the future to help us deal with some problems with running out of addresses. But there actually are addresses at other layers as well. Another address that's important is at the data link layer. There's something called the MAC address. Some of you who get into gaming and needing to filter certain MAC addresses or forward certain ports at the transport layer, we'll get into this information in a little more detail. But the most important address is at the IP address at the network layer. So here's a question I always ask. If you were to send a message and go to the other side of the internet, however you define that, how long would it take to get there? Well, there are tools out there to test that out. And unfortunately, at the time of the creation of this video, the university has actually started blocking this tool, and so I can't get a good information to show you visually what's going on, which is odd. But you can kind of use the command, the trace route command on Windows. You can put in a website using the trace route command and kind of see what happens and see how a message gets kind of hops across the different routers on the internet. And most people are surprised to find out, well, how many hops does it really take to get somewhere on the internet? Most places on the internet can be, can go in somewhere between 10 and 30 hops, 10 and 30 devices between you and your destination. Sometimes it's a little bit less than that, and sometimes it can be a little bit more to get to the other side of the internet, whatever you define that to be. But the internet actually isn't have that many different stops as you're moving along it. There's the internet backbone is fairly well standardized and consolidated, so it doesn't actually take that long to get to the other side. All right, so we've talked about this a little bit in depth, but let's specify things here. So what a router does. A router determines which path a particular message or packet should take as it goes through the network. And the way that it does that is it uses something called a routing table. So it keeps a little list internally. It's an own little table. It's kind of a mini database that it uses to make routing decisions. So when a message comes in, it looks at that message, looks at its routing table, and goes through the rules in its routing table to decide which way a message should take. Should it go, like in the last example, to Dallas or to LA? The router makes that decisions. And again, these tables are a little more complex than I'm talking about here, but I'm just talking about the basics for this particular class. So here's a couple of examples of routers. This is on the left-hand side, there's a Cisco router. It's an enterprise-grade router. On the right is an old Linksys router, which is kind of the poster child of consumer-grade routers. And each of these does basically the same job, just the left one can handle more traffic and more complexity and more complex decisions. All right, application layer. Again, we talked about this kind of first, and now we're kind of coming back to it towards the end as we talk about applications and use of networks. So here's, again, an example of what a client here, the client's on the left-hand side, this little laptop here, it wants to retrieve a website. So it's got a web browser. The web browser creates an HTTP message. That message goes and uses the other layers to go across the internet. Oh, skipped over our web server. Looks like it went too far. But anyway, it went to the other side of the internet. And then the web server, it knows what to do with that. And then it will then craft a response message. Again, send it using the other layers all the way across the internet, all the way back to our client. All right, and so our client receives that information and then knows how to deal with it. Email is a little bit more complicated, but not too much. Let's say we have two devices that are on the same server. You've got your client, and you want to send a message to your friend who's at the same university, and you use that client to send a message, and it goes over to the mail server. The mail server then stores that message. It keeps it there until the client goes and requests that message using a protocol called IMAP or POP. And it requests that message and say, hey, mail server, send me that message back. And the mail server says, oh yeah, I know what you're talking about, IMAP or POP, and it goes and sends that message to your client, and then your client then displays that message. Now, in web email and in email generally, this is getting a little more complicated than this message, and we talk about this in my advanced class in more detail. But that's kind of the basics of how email has been running at a basic level. All right, let's now define the internet. The internet is by far the most used network in the world. It is an internetwork. An internetwork is a network of networks. Okay, it means we have networks that are connected together. Now, the internet is a particular internetwork, and it happens to be one that is run by a lot of different organizations, and that's one of the things that makes it really unique. Some of these organizations are not-for-profit organizations or nonprofit. Some of them are for-profit. In fact, most of them are for-profit, organizations, companies. Many of them are governmental institutions. And yet, even though we've got these different organizations that are all working together, it still actually generally works, which is a really interesting aspect. One of the reasons that it works, we'll come back to that slide, one of the reasons that it works is there are some very strict standards that we use, like TCP and IP, for example. You want to participate in the internet, you've got to run TCP and IP. And those standards are those rules, those languages are kind of, in some cases, set in stone. All right, so that each organization has to follow certain rules, even though they, might follow different rules for other things. So behind the scenes, here's a picture of how the internet works. Another way of thinking about the internet is that it can be a network of internet service providers, or ISPs, and their customers. In fact, that definition might even be a little more accurate. Now, internet service providers come in a couple of different, a few different types. We have the really large ones, the really, really large ones. And those are called Tier 1 service providers. There's really only like anywhere between 8 and 10 of these worldwide at any given time. These are the really, really big providers. And then we have kind of the next tier providers. For example, Comcast is a Tier 1 provider. Verizon is a Tier 1 provider. Then we have a Tier 2 provider. Now these ones tend to be not as big as the Tier 1 providers, but they're still very large. They're still important. These are providers like Time Warner Cable and Cox, and there's a few other large providers, but not enormous providers. And then we also have Tier 3 providers. Now these are the small internet service providers, the regional ones. In this area we've got CCI, Consolidated Communications, which used to be called Sure West. That's a local one that's a Tier 3. Frontier is another Tier 3 internet service provider. And these providers all connect to each other. And they do something, they share their data at places called Internet Exchange Points, or IXPs. And so you connect to your provider, but then they connect to each other at Internet Exchange Points. Here's another related example of various different ways to connect to the internet. Okay, we have things like our DSL, different types of DSL. Hopefully nobody's on dial-up anymore. We have cable internet. We have, in this case, different types of leased lines like a T1 or a T3. We have other types of Ethernet-based. I don't see fiber on here, but we might have fiber optic connections to our various different ISPs, and then they connect with each other at the internet exchange points. Now, we've talked about the internet. Wide area networks. The main difference there is how the circuit connects together and the type of customer. Wide area networks tend to be almost exclusively business customers, and so there's service level agreements and there's different types of technologies for that. We've already talked about there's different ways of connecting to the internet. We've talked about DSL and cable. In some locations, fixed wireless is useful, especially in rural areas. And then mobile wireless is becoming more and more important, as people are using, instead of, traditional ISPs, they're using their Verizon, AT&T, Sprint, T-Mobile, or whatever MVNO they use to connect to the internet. And there's a few other options as well. I'm not going to go into the details on this, but here's some examples of how cable and DSL works in order to connect. And so you've got, you've got your subscriber premises and your cable modem, and then we connect there out to our provider, our internet service provider's location, and then we connect to the internet from there. Similar, DSL is very similar on the other side. It's just we connect using different technologies. All right, a pet peeve of mine. The internet and the World Wide Web are different. They're not the same thing. The internet is the transport mechanism. It's the way we send data back and forth. Whereas the World Wide Web is the content and the applications that use the internet, right? So while it is not incorrect to say that you are using the internet to watch a video, the internet isn't really the video or the content there. It's the transport mechanism behind the scenes. So just be careful on that. I usually ask an exam question about it. All right, let's talk about a couple of uses of internet. One of them that many students, well, in my experience, usually about 10 to 20% of students have used them extensively in the past, and the others maybe either haven't used them or haven't even heard of them. Something called a VPN. So a VPN is an important device, or sorry, an important piece of technology that allows, and here's the details, you don't need to know all of those details, but the way that VPN works is, let's say that you are an employee and you've got a computer, maybe it's your work computer, and let's say you're on the road and you need to connect to some data that's on a server somewhere in your office network, okay, down here. But you're not on your office network, okay? You're nowhere near. Maybe you're a traveling salesperson, or maybe you're on the road, doing some work at a client's location, but you still need to connect. How can you make that work? Well, this is what VPN does. VPN says, okay, I'm going to take all of the traffic, the network traffic on your computer, and I'm going to wrap it up. Technically, it's encrypting it, but I'm going to wrap it up into what I call a VPN tunnel. Okay, and I'm going to send it out across the internet, and it's going to be wrapped up in the tunnel. All of the traffic, everything. And if it connects properly to my Office VPN software, okay, sometimes this is hardware also, but software, what this software will do right here is it will spit out your traffic onto the local network as if you were already a device, a computer, that was directly connected to the Office network already. So all of your traffic looks like you're on your Office network. And even if you go to the internet, for example, you actually go through your Office network and then back out to the internet from there. And so this is very useful for a number of different reasons. You know, it helps keep things secure, you know, so people can't snoop on your traffic if it's encrypted using VPN. It allows you to access resources across the network. Some people use it for pretending they're in certain countries. For example, I know it was a big deal that people from foreign countries would want to connect to Netflix, even if Netflix wasn't allowed in their country, and they would VPN into a US-based VPN provider or proxy service and allow them to connect to Netflix. Netflix has been cracking down on that, but VPN is a very useful tool. It also can be used to connect multiple buildings together. So rather than pay for an expensive wide area network, let's say you have 2 offices in the same city or in the next city over, you could use VPN technologies to connect those offices as if they were directly connected with a cable. All right, we're going to come to net neutrality in our next class and have a debate about it. Just want to remind you of that. Telecommuting. Let's talk telecommuting for just a minute. This is a really important managerial thing to consider. So telecommuting is the concept that you can work remotely, oftentimes from home, but it doesn't have to be from home. And this work is enabled by our various different data communication technologies. But is this a good thing or a bad thing? Is it a good thing to be able to sit in a kiddie pool and do some work? Well, as it turns out, most people who are telecommuting tend to like it a lot. They also, on average, tend to be more productive and actually tend to work more hours of the day than those who don't telecommute. It's considered to be environmentally friendly, part of a green IT kind of practice, because telecommuters aren't commuting and producing, you know, carbon emissions, for example, not using electricity at their employer's location, and so it often is putting less strain. It also allows companies to maybe even downsize their offices. If people are not coming into the office, maybe they can use a smaller office with a smaller footprint. Now, on the flip side, are there any negatives of telecommuting? Well, as it turns out, there potentially are. Sometimes you see employees who are, you know, slacking off and not doing what they're supposed to, but that's actually not very common. What you do see, though, is some employers do feel lonely. They do feel disconnected from their office employees. They don't get to go out to lunch or see people at the water cooler kind of conversations. They may, in some cases, be passed over for promotions or raises. And so some companies that are, you know, aware of this kind of issue, Apple, for example, I know does this, they will put their telecommuting employees in a different pool than their non-telecommuting employees when they do promotion and raise decisions, so that they don't pass over people who are telecommuters simply because they don't know them as well because they aren't in the office all the time. Now, this is a little bit of a controversial thing, telecommuting. Google's not a huge fan of telecommuting. Yahoo banned telecommuting a couple of years ago, and that was a controversial decision because they used to have a lot of telecommuters. And so there's pros and cons to this, but it's an important managerial decision that for employers to make. Now, the cloud. What is the cloud? The cloud is a buzzword, but it's also a set of products and services. I joke sometimes, I love our marketing students, but I joke sometimes that cloud computing is what happens when a marketing student takes an MIS class, simply because cloud computing existed long before it was called cloud computing, but now it's a really big deal because it's got a really cool, catchy name. So let's talk about what cloud computing is. Cloud computing is when we take our infrastructure, and that's a hard term to define, but let's say our hardware and software, and we let someone else run it. So our data and our servers and our software gets run by someone else, or maybe our network gets run by someone else. It's when we take all or part of our infrastructure and send it to someone else, and that service and infrastructure is accessible over the internet. But there's pros and cons to this. Now, one of the benefits, and possibly one of the drawbacks, is cost. Now, let me explain why I put that on both lists here as far as benefits and drawbacks. If you're really not very good at IT, going to cloud computing is like outsourcing to a good provider, and you might save a lot of cost. But if you're really good at what you do, well, moving to the cloud might actually cost you more money, especially in the long run, because, well, the cloud computing provider is still adding their markup. They've got to make a profit off of it. So if you're as efficient as they are, well, your costs are going to be lower. So this really depends on your organization. Now, cloud computing providers, especially the largest ones like Amazon and Microsoft and Google, etc., tend to be very reliable. And so that's very helpful. It's a big deal when, for example, Amazon goes down, half the internet goes down, and it seems like, or at least half the content on the internet goes down. Another huge benefit is scalability. What happens if you're a small company that thinks it's going to make it big? What happens if you make it big? Is it going to crash all your servers and crash all your things? Well, if you use cloud computing, you might be able to scale up and just pay for when you use the services. Amazon, for example, if you need more servers, Amazon will fire up more servers for you, and they'll only charge you on the numbers of servers they fire up for you. This can be a great benefit, especially if your company has strange, especially seasonal scalability needs. Maybe your Hershey chocolate company, right? And you have some very distinct seasonality, right? You're really, really busy for Valentine's Day and for Halloween and for, this is times that aren't always, big seasons for other companies. And so that can, cloud computing can help you with that scalability. Now, I also put security on benefits and potential drawbacks. Now, the cloud computing providers tend to be more secure than your average IT organization. But it depends on your cloud computing provider. What happens if you choose one that's poor or not very good at security? This could be a potential drawback, so you've got to be careful on that. Performance tends to be much better on the cloud, but it doesn't have to be. But on the drawback side, you kind of lose control. What happens if the cloud computing provider does things that you're not happy with? Especially what if it's your software on the cloud? There's some providers, we'll talk more about this with, for example, Salesforce later. What happens if they make changes that you don't like? Well, you kind of lose some of that control that you would be able to change, or not change if you had it locally. Here's some examples of storage cloud computing providers. Microsoft, Google's Google Drive and Dropbox, and Microsoft's OneDrive and Box. These ones are highly visible. Students tend to be fairly aware of them, but they're really only a small portion of overall cloud services. So be aware that there's a lot of other things out there, and we'll talk more about some of these later. As an example organization, let's talk about Amazon. Amazon is one of the largest cloud computing companies, and in terms of gaining revenue as a cloud computing company, they are by far the largest. So, in fact, they used to be, a couple of years back, they were 5 times larger than their next 14 competitors combined. But recently they are facing a lot of competition, especially from Microsoft. Google's trying to get in the game and trying to undercut them on price. We'll see how that goes. But they do a lot of infrastructure as a service. So rather than having software as a service, they mostly focus on servers and IT infrastructure. And we can look online, we can look at some of their various services. They have a lot of them, and they're expanding them all the time, and they do a really good job. Here's, for example, the list of Microsoft services and which data centers they offer them in. And you can just go down the list. There are a lot of different services that Amazon provides, and these are very important. For example, their Elastic Cloud Compute and things are extremely important for many organizations out there. They have databases and web servers and storage and all sorts of different types of cloud computing services that they provide. Another example organization is Cisco. Cisco is probably the most widely known networking gear company. They provide routers and firewalls and other sorts of in-network access points, network infrastructure. They're a San Francisco-based company, and a very, very important one. For a while there, they were the largest market cap company in the world, but then they're still large, but they've fallen off a little bit. And they're a really interesting organization because they grow mostly through acquisitions at this point. And so they've been acquiring some really interesting companies and started to move towards Internet of Things more and more. We'll talk more about that as part of some of our other discussions. So next class, I want you to be aware that we're going to have our net neutrality debate. I'll also do some show and tell, but then be aware that we're going to go and do, after that, we'll do enterprise systems. So make sure that you do the readings for enterprise systems, and as well as that, do the questions for enterprise systems. All right, and so that is a very long lecture on networks, data communication, and then we'll wrap it up with our debate next time.